Hi, everybody. Welcome to Unit 4, Acids, Bases, and Acid-Base Equilibriums. So we're going to kick things off with a little bit of a review of acids and bases and calculating pH. So take a second to look at the warm-up question. I want you to pause the video and just see what you can remember about properties in acids and bases that we've taken a look at in the past. And then when you're done, come on back. Okay, so let's talk about what an acid and a base is according to some definitions. So the first definition that we had of an acid and base was the Arrhenius definition. So according to Arrhenius, he said that an acid is a substance that increases hydrogen ion concentration. So when he's talking about hydrogen ions, the hydrogen ions really is a little bit of like a simplification of what's actually happening. So when an acid dissociates, it's usually it's always into water. And those hydrogen ions don't really stay free hydrogen ions. Instead, what happens is they actually bond to the waters that are around them. So when we write hydrogen ion concentration, you may see it written like this, but what's really actually happening is those hydrogens are bonding to waters to produce this ion right here. This is called hydronium. But essentially, it's the same concept. You're increasing the hydrogen ion concentration in the water because you're increasing the positive charges that are in the water. So an acid is a substance that increases hydrogen concentration. So alternatively, you would have a base. A base is going to be a substance that increases hydroxide ion concentration. So instead of having a bunch of extra positives, now you got a bunch of extra negatives. So base is going to increase your hydroxide ion concentration, which we will write like this, OH minus. So here's our hydroxide. Okay, so let's take a second and actually get some practice identifying Arrhenius acids and bases. So I've got 4 substances for you here. HNO3 is our first one. So we're going to take a second to decide, is this thing an Arrhenius acid, a base, a salt, or a molecular compound? So according to Arrhenius, an acid is something that increases hydrogen ion concentration. And if we look at HNO3, we see that little hydrogen attached right there. So when this thing dissociates in water, that means it's going to increase hydrogen ion concentration. So this must be an Arrhenius acid. All right, BALOH3. Okay, so do we see any just plain old hydrogen sitting around? No. So next up might be an Arrhenius base. So according to Arrhenius, a base is something that increases hydroxide ions. And ooh, look, I've got some hydroxides right there. So this must be an Arrhenius base. When this thing dissociates in water, it's going to increase the concentration of hydroxide. All right, moving on to CaLNO3. Okay, is it an acid? Do I see any hydrogens? No. Okay, is it a base? Do I see any hydroxides? No. All right, next up on our list is a salt. So a salt is just a general word for any ionic compound. Ionic compounds are made from a cation and an anion, and I have right here a cation and an anion. This must have come from aluminum 3+ bonding to nitrate, NO3 minus. So this thing must be a salt. It's not going to increase hydrogen ion or hydroxide ion concentrations, and it meets the definition of an ionic compound. All right, last one, NH3. All right, do I see any free hydrogens available to leave? No. Do I see any hydroxides? No. Is it a salt? No, because nitrogen and hydrogen are both non-metals, so they must be bonding covalently, and we call covalent compounds molecules or molecular compounds. So this meets the definition for a molecule. Molecular compound. All right, so the other thing I want to point out when I said free hydrogens earlier, this thing can't dissociate into water because it is not bonded ionically, it's bonded covalently. So that's the other reason why I know it's not free hydrogens in there that I can't dissociate. So this thing must be molecular, it's a covalent compound. All right, so here's the issue with Arrhenius acids and bases in their definitions though. We just classified these 4 substances, fine and dandy, but it turns out that NH3 actually exhibits properties of bases. It feels slippery, it has a pH greater than 7, and when you add phenolphthalein to it, it turns pink. So I gave you some hints up here that you can use to check your answers, to see if you got some of those base properties. But NH3 ammonia, has properties of bases. So our Arrhenius definition isn't very good. If this thing is a base, but it doesn't increase hydrogen, if this thing doesn't increase hydroxide ion concentrations, we need a better definition. So Bronsted and Laurie came up with one that was way better, and this is the one that we mostly use today, the one that we will mostly use today. There is one more definition of acids and bases that's also good, but we're not going to get into it. All right, so Bronsted and Laurie said that their definition was an acid is some substance that donates hydrogen. So let's take an acid that we know of, HCl, hydrochloric. So hydrochloric is an acid. If this thing reacts with water, what are we going to get? We're going to get H3O plus hydronium and Cl minus ions floating around. So how does this thing meet the definition of a Bronsted-Lowry acid? HCl is going to donate its hydrogen from its formula, HCl, to the water. So this thing is going to give up its hydrogen and produce hydronium by donating the hydrogen to water. So alternatively, a base is a substance that accepts hydrogen. So acids donate, bases accept. So let's take a look at that ammonia. We got NH3. We're going to react it with water. And what are we going to get? Well, if NH3 is a base, this thing needs to accept a hydrogen from its acid. So here water is acting like an acid. So if NH3 takes on another H, we're going to get NH4. What's going to be left over? Well, water gave up NH, so it only has one left. So its formula is going to be OH. So hydrogens have a 1+ charge. So if ammonia is taking on a hydrogen, it's going to have an extra proton. So it's going to get a positive charge there. OH, it's losing one positive charge. It's getting rid of a hydrogen. So this thing's going to have a minus charge left over. So ammonia is acting like is a base, acting like a base, according to the Bronsted-Lowry definition, because it's accepting a hydrogen from that water. Water is acting like an acid because the water is donating that hydrogen to the ammonia. So when this happens, you have an acid reacting with a base. You produce 2 new species at the end, and we give them names as well. So when a base receives an H+ ion from an acid, so our ammonia is our base receiving an H+ from water, it's effectively going to become a new acid because now it has that extra proton that it can donate back. So we call the remnants of that original reactant base the conjugate acid. So the base takes on a proton, and now it itself can act like an acid to donate that proton back. So we call it a conjugate acid. So then if similarly, if you have an acid, that thing loses its hydrogen, it donates it, and it has the potential now to gain a hydrogen back. So like with up here, our HCl was our acid, it donated it, and it produced Cl minus at the end. Now that thing's got a negative charge, it can look to take in a hydrogen back in to reform that HCl potentially. So the remnants of your original reactant acid we call the conjugate base. So let's use this reaction here as an example. So you have NaOH reacting with, this is acetic acid, to produce these three substances at the end. All right, so think about which one's going to be our acid or our base according to the Bronsted-Lowry definition. Well, this thing right here's got a hydrogen right on at the end. This thing's got an OH right there. So this must be our acid. This thing can donate its hydrogen. You can also get a little bit of a hint when I give you the products too, to look to see which one loses a hydrogen or which one gains. So here, this thing is going to lose its hydrogen. It's going to donate it. So that means that this must be our acid, and this must be our base. So I'm going to label those right underneath. So when our acetic acid donates its proton, it produces this ion right here, acetate. So the conjugate acid, acids and bases will always form their conjugate acids and bases in pairs. If you have an acid, it will form a conjugate base. So this will be our conjugate base. Now that it's got that negative charge, it's lost that hydrogen, it can add an extra hydrogen back in, it can accept, so it must be a base. Over here, we've got our base. This thing's going to accept the hydrogen from the acetic acid. And what's it going to form? Well, it's going to form these two things. Sodium hydroxide is a salt, right? So when we dissolve it in water, it dissociates into its ions. So the OH part is going to pick up that hydrogen from the acetic acid to form water. And we're left over with just some sodium ions in solution. This thing doesn't really matter. It doesn't really participate in our reaction. So we call it a spectator ion. So we've seen that word before, and in acid-base reactions, what you can typically expect is if your base is some sort of salt, you'll have some sort of spectator ion present because you won't need that cation, very likely. All right, so back to NaOH. NaOH is our base, so that thing's accepting a hydrogen from the acetic acid, which means we are now forming the conjugate acid right over on that side. That water can lose that hydrogen, it can donate it back over. So when we're talking about conjugate acid base pairs, one thing that I do want to make super clear is that conjugate acid conjugate base pairs, or acid conjugate base, base conjugate acid, you know what I mean, they have to differ by one hydrogen. We will see some examples of acids that are diprotic, which means when we say protic, we're talking about protons, so two hydrogens. And it can lose both of those hydrogens, but if we're talking about its acid and conjugate base pair, it only must differ by one hydrogen in order to be considered that conjugate acid base pair. Okay, so let's get a little practice. Identify acid, base, conjugate base in the problems below. So take a look at A. We've got HF plus Cn minus reacting to form HCN and F minus. So which thing is going to give up? Which thing is going to take? Well, we see that our HF is becoming F minus in the end, so this must be donating its proton. Also, CN doesn't have a proton, so that's another way you can try to figure that one out. So HF is the only one that has a hydrogen, it's the only one that has a proton, so it must be our acid. So this thing is going to form F minus at the end, so this must be its conjugate base. This makes this our base. It's ready to accept a proton, and so it's going to form this conjugate acid, and those are our conjugate acid base pairs. All right, now for the next one, I'm going to do one of these with you, and then I want you to try the other three, and then check your answers. So take a look at this first one here. You're given a conjugate acid or a conjugate base, and then you want to try and find what its pair would be. So the conjugate acid here, this is oxalic acid, H2C2O4. So if this thing wants to form a conjugate base, how's it going to do it? Well, it's going to donate a proton. It's going to lose a proton. So over the little barrier right here, I'm going to say we're losing an H+. So if we do that, we still have one H left over. Our formula just becomes HC2O4. So we are changing charge here. Look at this thing right here. It has no charge to it, which means that it's neutral, but I'm losing something that's positively charged. I'm donating a proton, so my conjugate base has to have a charge on it, and what charge will it have? 1 minus. I got rid of 1 positive, so left over, I now have a negative charge. I have a hole to fill. All right, so try these last 3 on your own, pause the video, check in with the answer key, and then come back. Okay, so then the last thing that we're going to talk about today is strong versus weak acids and bases. So we're going to do a lot of work in this unit with weak acids and weak bases in a lot of equilibrium problems. But this is going to be a little bit of review of strong acids, strong bases, since we've actually seen these examples before. So strong acids, we can say completely ionize in water. So they completely dissociate to form their ions. So what would this look like? Well, it looks like that example I showed you earlier. HCl is an example of a strong acid. This thing can react with water to completely ionize. It'll form hydronium ions and our chlorine minus. So just a reminder, here's our acid, here's our base, here's our conjugate acid, here's our conjugate base. So why is this important? Because if the strong acid completely ionizes in water, let's say it started out with a concentration of 1 molar, the concentration of our conjugate acid will also be 1 molar because all of the acid has dissociated. So the big 6 strong acids that I want you to try to memorize are the ones that are on this list. These are super important because if you see these things, you know they will completely ionize. It makes calculations for them much, much easier. Weak acids, however, are a little bit tougher because weak acids only partially ionize in water. So what would this look like? So let's say we have something like acetic acid again. CH3COOH. This thing's going to react with water, and it's only going to partially ionize. So what that means is we need our equilibrium arrows. We're going to go through that forward reaction to get some acetate, but not all of it's going to ionize, and we can go back and forth. We can reform some of that acetic acid as we're dissociating that acetic acid. So here's our acid, here's our base, here's our conjugate base, here's our conjugate acid. So why is this important? Because if we're starting out with a 1 molar concentration of acetic acid and it's only partially ionizing, that means that the concentration of our conjugate acid should be less than 1 molar. But we don't know exactly how much unless we have some more information that we can use to figure out a concentration from some equilibrium calculations. So, strong bases and strong bases and weak bases. Here's the crazy thing. Strong bases, how can we define them? They also completely ionize in water. Same definition, just a base instead of an acid. So what do you think a weak base definition is going to be? You guessed it. Weak bases partially ionize in water. So if we want to write out an equation for a strong base, I'm going to pick one of our 6 strong bases that I have in the table right here. So most of your hydroxides are strong bases. They've got that OH on there. They completely dissociate to break apart into their ions. Since we did just recently learn and talk about solubility a lot, you may be thinking, according to your solubility rules, something like calcium hydroxide, we said was insoluble, right? But we also learned that insoluble is kind of a general term, or kind of like a misnomer term, where insoluble salts can still ionize in solution. So it's still considered a strong base because that thing will break apart to release free hydroxides in solution. All right, so let me give you an example of a strong base dissociation. Let's do potassium hydroxide, KOH. Here's our base. This thing is going to dissolve in water, so I'm going to put that H2O right above that arrow saying I'm dissolving it, and this thing's going to break apart into its ions, K plus and OH minus. So again, because this is a strong base completely dissociating, if we start out with a 1 molar solution of this, our base that we're going to get, our conjugate acid concentration is going to be 1 molar as well. For weak bases, something like NH3 ammonia, I put this into water. It only partially ionizes, so I have to use my equilibrium arrows. And then we have seen this reaction before as well, but why is this important? Same reason as the one before. If this thing starts out as a 1 molar solution, this thing's going to have a less than 1 molar concentration, so we have to do some equilibrium calculations. All right, so there's your quick intro for some of you, review for some of you, for acids and bases.